Okay, let's unpack this. It feels like one of the most monumental topics defining modern life. Human control versus automation.
It really is.
We're living in this world where AI systems are making decisions for us in realms that, were once exclusively human. We're talking about everything from piloting our planes to flagging defects in a factory, even deciding if we get a loan.
It's the ultimate trade-off, and one we are, I think, navigating without a clear map. Automation promises these incredible gains efficiency, speed, safety improvements, especially in really complex, highly repeatable environments.
Right.
Just think about an autonomous system confidently landing an aircraft in what they call Category 3 visibility.
Which is basically zero visibility.
Essentially, yeah.
Yeah.
That's a gain that no human pilot, especially under fatigue, can consistently match.
Yet, and this is the core tension we're diving into today, those exact systems, the ones designed to eliminate error, they simultaneously erode the very human agency we need for oversight and, crucially, for accountability. So our mission is clear. We need to cut through all the noise and really try to figure out where that critical balance point lies. Where do we draw the line to maintain what philosophers and engineers are calling meaningful human control?
And we can't start this deep dive in the engineering lab. We have to start in the philosophy department because the first casualty of automation is often the moral dimension.
How so?
Well, when we delegate a significant action, especially a high-stakes action, to an autonomous system driven by AI, we fundamentally reduce human agency, our power to, translate our intentions into actions and then take personal responsibility for the outcomes.
And this reduction in agency leads us right to the defining ethical problem of this whole revolution, the responsibility gap. I've heard this term a lot, but what exactly defines that gap and why is it so hard to close?
The term was coined by a philosopher named Matthias back in 2004, and it just perfectly encapsulates the dilemma. Undesirable things happen because of technology, people get hurt, property is destroyed, yet no single human can be held morally or legally accountable.
Because the responsibility is so diffused.
It's completely diffused. The designers will claim, well, we created a rule-based system, we can't predict how it'll evolve. The manufacturers say they just assembled the parts, and the operators, they claim they were just following the system's instructions.
So accountability just scatters across the entire chain until it basically dissolves. It leaves victims without any recourse and society without any sense of closure.
Exactly.
And this is where it gets really interesting, because this gap attacks the philosophical bedrock of what moral responsibility even is.
Yeah.
We have to go back thousands of years to the core conditions.
That's right. I mean, if we look at the traditional framework for assigning moral responsibility, going all the way back to Aristotle, there are two conditions that have to be met for us to assign blame or praise.
Okay, lay them out for us.
The first is the control condition. The agent must have control over the behavior that led to the bad outcome. It sounds simple, but it's foundational. If I didn't actively control the action, I can't be held responsible for what happened.
Makes sense. And the second?
The second is the epistemic condition. This is about knowledge. The agent has to be able to foresee the potential negative consequences of their decisions. It's not just could you control it, but did you know what could possibly go wrong? Did you have the knowledge to intervene?
And the power of modern machine learning, the complexity of things like deep neural networks, is that they seem almost designed to defy both of those conditions for any single human.
Precisely. We as humans might set the initial rules or the training data for an AI system, but machine learning allows those rules to evolve on their own through interaction with real-world data.
After it's been deployed.
After it's been deployed. And that evolution makes the system's behavior extremely difficult. In some cases, it's mathematically impossible for the designers or the manufacturers or the operators to fully predict or control.
So if I'm an operator, I can say, I didn't control that specific action, which challenges the control condition, and I can also say I couldn't possibly have foreseen that outcome based on the code I was given, which challenges the epistemic condition.
You've hit the nail on the head. Under our traditional theories of moral responsibility, if you can't fully predict or control the behavior of a system, the humans involved become morally blameless. The more complex the tech gets, the less human agency is exerted, and so moral responsibility just dissipates. It leads to this profound systemic gap.
Which brings us squarely into the psychological and, the moral costs of all this delegation.
Yeah.
If our responsibility is diffused and our agency is diminished, how does that actually show up in the real world for the human operator?
Well, the most observable effect is this loss of agency, which often results in what philosophers call technological moral luck.
Moral luck.
Yeah, we see it every day. I mean, just think about your experience with a GPS. When you're driving in a city you don't know, you're not actively navigating. You are, for all intents and purposes, just following instructions. You've delegated that cognitive control.
It's a really interesting psychological shift. When I'm relying on a GPS, I'm mentally checking out. I just trust that the machine knows best, often I have to admit pretty blindly.
And studies confirm this. As our reliance on technology goes up, humans tend to feel less responsible for the outcomes of those decisions. They might even actively shun accountability, saying, well, the system chose the dangerous path, or the system told me to turn left. Your personal sense of moral guilt just fades because you gave away the decision-making process.
But the moral kicker here is that society might still hold you responsible, right? Regardless of your personal feeling of lost control, if you hit someone while following a bad GPS instruction, you're still the one behind the wheel.
That is the very definition of technological moral luck. Situations where we're held morally responsible for things that are fundamentally beyond our control simply because we relied on a piece of tech to do something we used to do ourselves. The more we insist that control is a prerequisite for responsibility, the more we have to accept that with complex tech, moral responsibility becomes a matter of pure blind luck.
So the technology is designed to make us safer and reduce our cognitive load. But when it inevitably fails, the human operator is still the one caught in the liability spotlight. That sounds like a classic double bind.
It absolutely is, and it seems just unequivocally negative. But this is where our sources introduce a genuinely counterintuitive argument. Some researchers are suggesting that these responsibility gaps might not always be a bad thing. They could sometimes be beneficial for society.
Wait a minute, are we seriously suggesting we should welcome this kind of ethical fuzziness? That sounds like a really convenient excuse for developers to just avoid liability.
That's the essential question, and the concept they introduce here is the reverse tragedy of the commons of responsibility.
Okay, break that down.
So, the normal tragedy of the commons is when everyone acts in their own self-interest and depletes a shared resource, like a pasture. The reverse tragedy is what happens when we demand too much accountability from everyone.
So what are the consequences of just pervasive, excessive accountability?
Well, if we hold every single individual excessively accountable for uncertain risks, especially in high-stakes research and development, two things happen. First, no one is willing to take necessary risks. People become paralyzed by the fear of direct, crippling liability.
And
Second, individuals start discouraging others from taking risks because of the potential for joint liability down the line.
so if the potential downside is catastrophic personal or institutional ruin, innovation just grinds to a halt.
Exactly. To address huge existential risks like climate change, we might need high-risk, radical innovation like large-scale geoengineering projects. This kind of R&D has inherent risks of failure or unintended harm. If everyone involved, from the researchers to the funders, were exposed to excessive liability from day one, that kind of innovation would become impossible.
That puts the moral math in a totally new light. So refraining from excessive blame, allowing for a degree of forgiveness in these cases, can actually safeguard our ability to make necessary technological progress. It shifts the focus from, I guess, finding someone to punish to finding ways to learn.
It's a compelling instrumental perspective, yeah. It lets people focus on making the right long-term professional decisions, the right engineering choice, the right policy choice, without being overly concerned about the career-ending blame they might face if things go slightly wrong, which, in exploratory science, is almost guaranteed.
This philosophical discussion leads us to the really existential question of delegation, which is known as the tragic choice argument. And we're not talking about simple preferences here, are we?
No, not at all. Human life is just full of morally tragic choices. These are irresolvable conflicts where every possible outcome leaves some kind of moral taint, a remainder of regret or harm. There isn't enough data or logic to pick the single right choice.
That's where the psychological cost comes in. How do we typically cope with having to make those gut-wrenching, morally compromising decisions?
We cope in three main ways. First is illusionism, where we try to convince ourselves the choice wasn't tragic at all. Second is responsibilization, where we just internalize and bear the profound psychological cost ourselves, which often leads to burnout and anguish.
And the third?
The third is delegation, shifting that psychological burden onto someone or something else.
And this is where autonomous machines enter the picture, offering this A very tempting escape route.
Really offer a reduced cost form of delegation. When a machine, rather than a human, makes a morally tragic choice, say in a triage situation where lives have to be weighed, it removes some of the profound psychological cost for the human operator.
So we were basically outsourcing moral trauma to an opaque algorithm. We're giving the machine the job of bearing the moral stain.
That's the hard truth of it. In scenarios involving genuinely tragic moral choices, welcoming these techno-responsibility gaps might be justified because it alleviates the human burden. It allows a person to function optimally in the next crisis, rather than being crippled by the weight of the last one. It's a very uncomfortable argument, but one we have to confront. Machines can be ethically advantageous precisely because they lack moral feelings.
Let's move from that abstract moral dilemma to the concrete risks, which are felt most acutely in safety-critical systems, like aviation, medicine, and the military. We've established that automation is amazing until the moment it isn't.
And the potential for catastrophe really begins with defining the depth of this delegation. Automation isn't a binary thing, it's a continuum, what researchers call the level of automation, LOA.
I think a lot of people just assume automation means fully automatic, but it's way more nuanced than that, isn't it?
Absolutely. The LOA continuum, as defined by researchers like Per Sermon and Sheridan, runs from level 1, where the human makes all the decisions, all the way up to level 10, where the computer decides everything, acts autonomously, and completely ignores the human.
And in between, you have all these different steps.
All these steps, yeah. Like level 4, where the computer suggests alternatives, or level 9, where the computer decides but only informs the human if it feels like it. This just shows how complex the handover of control really is.
And the more control we delegate, the higher up that LOA scale we go, the more efficient we are. But the closer we get to what the research calls the automation paradox.
That paradox is critical. It's been observed over and over again. Automation reduces the frequency of accidents because it handles routine tasks flawlessly. But, and this is the key, precisely because humans aren't practicing those tasks, the severity of accidents tends to increase dramatically when a failure finally does occur.
Why is that? If the machine fails, shouldn't the human just step back in?
The problem is primarily behavioral. The pioneering researcher Earl Wiener observed this. Low automation leads to high workload and fatigue, which is dangerous. But high automation leads to a different but equally critical set of problems: boredom, complacency, and the profound erosion of competence and skills.
So if a pilot only hand-flies a plane for 3 minutes during a 12-hour flight, their ability to handle a complex, high-stress manual emergency just degrades over time.
The machine makes you lazy, effectively. And when it needs you the most, your skills are dull and your mind is elsewhere. And that leads us directly to this famous problem of the human being out of the loop, or OOTL.
All right.
OOTL problems happen when the human, who is supposed to be monitoring the automation, has dangerously low situation awareness.
So their understanding of what's happening.
Their complete dynamic perception of the environment and the system state. When the system fails in some unpredictable way, the out-of-the-loop human just lacks the awareness needed to intervene in a timely and effective way.
And the causes are pretty clear. They're not paying enough attention, they implicitly trust the machine, and the system often fails to communicate what it's doing or why.
Exactly. It's a recipe for catastrophe. Let's look at how this plays out, starting with a consumer system that highlights this automation bias at the user level. Tesla's autopilot.
Right. Advanced Driver Assistance Systems, or ADS, they're marketed entirely on safety and convenience. But for the driver, learning the system's limits is completely ad hoc.
That is the core issue. Drivers build up trust very quickly, often after just a few positive experiences. And critically, there are no standardized exams or certifications required to operate these systems. Information often comes from a note in an over-the-air software update. They establish a very quick and often unwarranted baseline of trust.
And this unwarranted trust quickly manifests as dangerous behavior.
It does. The 2016 fatal U.S. accident involving Tesla's autopilot is the classic cautionary tale. The investigation found the driver was watching a movie and had ignored multiple visual and auditory alerts to keep his hands on the wheel.
And the system itself failed.
The system failed to distinguish a white trailer crossing the road against a bright sky, resulting in a collision. The driver's complacency was a direct result of automation bias, this uncritical trust in a system that was only semi-automatic. He ceded control, believing the machine had it all covered.
That shows the failure at the user level. But let's look at a failure where highly trained users were involved, but the system design itself actually induced the fatal outcome. Air France Flight 447 in 2009.
This is a textbook case of failure at the technical design level. AF447 was a highly sophisticated Airbus. When its airspeed sensors iced over, the autopilot just suddenly disconnected. The pilot flying, reacting incorrectly to that loss of automation, inadvertently stalled the aircraft, which then plunged into the Atlantic.
The big question was, how could highly trained pilots with a computer screaming stall, stall, stall at them not recognize that fundamental aerodynamic state?
The answer is cognitive overload, or what some call infobesity, right at that critical moment of handover. When the autopilot shut off, the flight management system immediately presented the pilots with a flurry of alerts and warnings, all at the same time, a massive information dump.
It was too much.
The post-accident analysis concluded that this cognitive cascade made it overwhelmingly difficult to recognize what was happening.
So the automation failed, and then the system's design actively confused the humans, making effective manual intervention nearly impossible. The sheer volume of information just defeated the entire purpose of keeping a human in the loop.
Exactly. The human was technically there, but their meaningful control was nullified by poor interface design and a lack of information hierarchy. Simply keeping the human in the loop isn't enough. Clear, non-overwhelming communication during a failure is the crucial weak point.
And that weak point is heavily influenced by the organization that dictates the training and the doctrine. Which brings us to the military case studies, the difference between the Army's Patriot system and the Navy's AGS system.
Here we have two highly complex missile defense systems with similar tech but wildly different operational outcomes based purely on organizational culture.
Let's start with the Army's Patriot system. What was their organizational bias when it came to automation?
Their bias was strongly towards automation. Doctrine actively encouraged operators to use the automatic engagement mode, and critically, their training emphasized rote drills versus the exercise of high-level judgment. The culture conditioned operators to trust the system without question.
Even in ambiguous situations.
Even in ambiguous situations. And the tragic consequence of this automation-first mentality was seen in incidents like the 2003 fratricides. This culture meant that a semi-automatic system, in the hands of inadequately trained staff, became a de facto fully automated system. Operators were nominally in control, but their judgment was so eroded that they ceded responsibility to the algorithm, resulting in lethal errors.
Contrast that, then, with the Navy's AGI system.
Mm.
It sounds like they basically wrote a love letter to human oversight into their operating manual.
That's a good way to put it. The Navy's doctrine has a clear bias towards the human. They prefer human decisions. Even in autonomous modes, an air engagement involves multiple qualified sailors officers and enlisted for track identification. They build in redundancy and explicitly train people that the system elements can fail, creating a necessity for human oversight.
So technically, both systems could launch missiles without human input. But the organizational policy and training determined where the real control lay. One system encouraged operators to think, the other encouraged them to just follow the drill.
Precisely. The organizational culture is the primary shaper of automation bias. Neither approach is perfectly fail-safe, but the difference in doctrine highlights that the level of trust in automation is a policy choice, not just a technical necessity.
Finally, let's look at a failure caused not by complexity or speed, but by the design of the interface itself, a failure that caused statewide panic, the 2018 Hawaii missile alert.
A very sobering example of how poor human factors engineering can just eliminate meaningful control even when the human is physically present and acting. This wasn't a complex AI failure. It was a simple human-machine interface error in a critical system.
A drop-down menu caused the terror.
That's right. The flaw was a simple drop-down menu on a computer screen that lacked clear visual or structural distinctions between the test environment and the live alert environment. The employee, likely under pressure, clicked the wrong option.
You mean to tell me a massive statewide nuclear threat alert was triggered because of a poorly designed menu? That's terrifying. It feels like the system was designed to trick the human into making an error.
It was an operational design failure, and the implication is profound. Even when a human is technically in the loop, meaning they have the physical ability to push the button, poor ergonomic design can effectively remove their meaningful control by making the correct action so hard to distinguish from the incorrect one. The failure wasn't in computation, it was in communication and clarity.
We've established that automation carries these profound risks when the human element is neglected. But we have to balance that by looking at where automation is succeeding dramatically, particularly when it leverages AI's unique strengths in data analysis and scale.
The healthcare sector provides some of the clearest, most valuable success stories, especially with autonomous AI systems used for diagnostics. A fantastic case study is the detection of diabetic retinopathy, or DAR.
DR is a leading cause of blindness, and screening often requires a specialist, which is expensive and often hard to get to.
Exactly. So autonomous AI systems like iArt and Luminetic Score are now being used to screen for DR, often in a primary care setting, which bypasses the need for an immediate specialist visit. These systems just analyze retinal images and provide a diagnostic conclusion right there.
How do they compare to human specialists in terms of accuracy? Are they competitive?
Oh, they're extremely effective. The metrics are compelling. Studies show high diagnostic accuracy, with these systems achieving sensitivity up to 100% and specificity up to 96% against the reference standards. This high performance really validates their use as a reliable first-pass diagnostic tool.
That's a huge step forward. But the real-world benefits seem to go beyond just accuracy.
They do. One of the key findings is about patient adherence. Historically, in many systems, the rate of patients actually following up with a specialist after an initial screening might be as low as, say, 18 or 19%.
That's incredibly low.
It is. After AI implementation in primary care, where the diagnosis is immediate, adherence rates have been shown to improve dramatically to 55%, and in some studies, as high as 95%. This ability to integrate instant diagnostics into primary care saves vision on a massive scale.
And there's that fascinating, unexpected environmental benefit as well.
Yes, the ripple effects are far-reaching. By successfully screening patients at their local doctor's office, you drastically reduce the number of necessary in-person specialist visits. Studies suggest this could lead to up to an 80% reduction in healthcare-related greenhouse gas emissions from things like patient travel. It's a systemic win.
Moving from diagnostics, let's look at manufacturing, where quality failures translate directly into enormous financial costs. I mean, automotive recalls can run up to $600 million.
It's all about precision and scale. AI applications, specifically computer vision and predictive analytics, are being used to eliminate human error in inspection. This allows manufacturers to lower false negatives, missing a defect, by 40 to 60%, drastically improving compliance.
The sources mention a specific, powerful hybrid approach used by TSMC in their advanced chip fabrication.
TSMC offers one of the best models for human-AI teamwork. They pair AI-enhanced auto-defect classification with a crucial human-in-the-loop review. The genius of it is that the AI flags defects during the material processing, not just at the end. This shortens the detection cycle and significantly lessens the operator's cognitive load.
We also have a clear, cautionary tale illustrating what happens when you fail to automate compliance, the Johnson & Johnson vaccine production incident.
That 2021 incident was a massive, costly failure. A failure to investigate discrepancies in batch review practices at a plant led to the accidental miscombination of ingredients, destroying 15 million vaccine doses. It was a failure of oversight and documentation protocols, which are fundamentally human tasks that require immense focus.
So how does machine learning fix this vulnerability?
By creating a complex automated verification architecture. They use optical character recognition, or OCR, to digitize paper records, instantly cross-checking data against approved supplier lists, internal data, and material expiry rules. Real-time analytics contextualize all this and immediately check for deviations.
So it turns a chaotic, paper-heavy compliance process into an automated red flagging system.
Exactly. This proactive verification system prevents the kind of human oversight error that led to that massive incident. It shows automation isn't just about speed, it's about eliminating compliance gaps and organizational blind spots.
Now let's pivot from these micro-level successes to a macro-level risk that AI introduces: systemic risk in finance. This isn't about one algorithm making a bad trade. It's about the whole system destabilizing.
This is a unique and chilling danger that has largely been neglected in mainstream AI ethics, which tends to focus on individual responsibility or bias.
So what's the risk?
The problem arises when trading AIs start exhibiting detrimental pro-cyclical behavior. This happens because highly sophisticated algorithms often copy each other's models or use the same data sources. If every AI is relying on the same indicators and those indicators start flashing sell, they all hit the sell button at the same time.
It creates a self-fulfilling prophecy, turning a small market fluctuation into a cascade that destabilizes the whole market. It sounds like a historical financial bubble, but accelerated to the speed of light.
That's precisely the threat. The reliance on common data streams means they can enhance market trends detrimentally, leading to sudden, deep collapses. So the ethical analysis has to shift. We can't just focus on individual actions, we have to focus on the relations within the system, the complex, opaque interactions between thousands of human and algorithmic market participants.
This necessitates an entirely new approach based on the ethics of complexity. We've established that automation is inevitable, highly beneficial, but profoundly dangerous when human factors are ignored. The consensus solution is meaningful human control, MHC. But as we've said, just having a human present isn't enough. So how do we actually define and operationalize MHC?
Well, MHC is fundamentally a wider socio-technical concept. It requires more than just a human presence or an emergency stop button. It has to be built on core values: accountability, responsibility, and transparency.
So if I'm an engineer, I need to design the system not just for efficiency, but so that the interaction between the user and the system is transparent and traceable.
Exactly. MHE is achieved when, regardless of the system's complexity, you can identify and hold accountable at least one responsible human along the causal chain. And to do this, MHC relies on two critical philosophical conditions.
The first is the tracing condition. This sounds like tracing information back to the decision point.
It's a bit more specific than that. The tracing condition requires a traceable relationship between the system's decision-making and the technical and moral understanding of the relevant humans involved. It demands two things: that the responsible person has the relevant training, and that the system is designed to make it technologically feasible for them to act on that responsibility.
So it connects the human agent back to the initial moral decision embedded in the system.
Exactly. And the second condition is the tracking condition, which is often the most difficult one to satisfy. It's the idea of reason responsiveness.
The tracking condition demands that the system can be shown to be responsive to the human moral reasons relevant in the circumstances. This goes beyond just technical efficiency.
It's the difference between performance and principle. An autonomous vehicle shouldn't just track a passenger's preference for the fastest route, which might mean speeding. It also has to adhere to traffic laws and prioritize pedestrian safety. It needs to track the normative moral reasons, not just the user's preferences.
This framework sounds robust, but advanced AI systems complicate this because of the notorious black box problem. If I can't explain how the system works, how can I trace or track its decisions?
That opaqueness is a major threat to MHC. Advanced AI systems are often black boxes because their reasoning involves millions of calculations that are functionally opaque. You know the input, you see the output, but you cannot see the logical engine that converted A into B.
So even though they're just complex calculations, the sheer volume makes them unexplainable.
Correct. And this opacity severely decreases the operator's awareness of the reasoning behind an outcome, making it exceptionally difficult for them to anticipate behavior, especially in surprising situations. Without sufficient technical skill and transparency, an operator who just follows the machine's suggestion lacks meaningful control, even if they technically push the button.
That creates what's called the attributability gap. The value judgments in the decision, say denying credit, don't actually reflect a conscious choice by the human. The human is just performing a rote execution of the machine's verdict.
This is why designers have a profound ethical duty, a meta-task responsibility. It's their obligation to design the system so that the user's inquiry into its reasoning is not made impossible or unduly difficult. Transparency has to be a design requirement.
To make this actionable, we need to move beyond these static models of control, human in the loop, human out of the loop, to something far more dynamic. This brings us to the operational solution: variable autonomy, VA.
Variable autonomy is the ability to dynamically adjust the level of automation in real time. It's about building a genuine partnership where control isn't just ceded, but transferred clearly, with an explicit definition of roles and responsibilities. It has to be crystal clear who transfers control of what and when.
And there's an important distinction here, right? Adaptive versus adaptable automation.
Yes. Adaptive automation is where the system itself assigns the level of automation, maybe reacting to a drop in the operator's attention. Adaptable automation is where the human operator consciously assigns or adjusts the LOA, and research strongly suggests adaptable is better.
Why is human assignment better?
Because it lets the human anticipate and prepare for changes in their cognitive role. If the machine suddenly decides to take over, the human is often surprised and unprepared. If the human decides to relinquish or take back control, they can mentally prepare for that transition, which leads to higher trust and better situation awareness.
Let's apply this MHC framework to an everyday context where these opaque algorithms cause real-world harm: finance, specifically the Apple Card investigation.
This case is a perfect illustration of what happens when MHC is absent. The investigation stemmed from allegations that the credit lending AI system discriminated against women, giving different credit limits to equally qualified spouses.
And while they didn't conclude it was unlawful discrimination, they criticized some systemic failures.
Yes, a lack of transparency and poor responsiveness to customer appeals. Applicants were often met with the bureaucratic nightmare of being told simply that a computer said so. The system failed the MHC test spectacularly because it lacked the tracing mechanism needed to track the reasons for the outcome, and it failed the tracking condition because there was no responsible person who could explain or adjust the decision.
And the policy was that you had to wait 6 months to even appeal. That's the bureaucratic manifestation of an accountability gap.
An MHC framework would demand transparency by design. The system would require a clear tracing mechanism to log the variables used, and crucially, it would ensure that a relevant human actor, an underwriter, a compliance officer, could intervene immediately, not 6 months later, to respond appropriately.
The ultimate goal, then, is to incorporate these ethical requirements into the very architecture of the system, a principle known as trust by design.
Trust by design is fundamental to what's being called Industry 5.0, which emphasizes human centricity. It means embedding ethical principles like transparency and fairness into every phase of the system's life cycle.
And for safety-critical environments, the design factors have to be incredibly rigorous.
It must be. We need to prioritize 3 key things. First, ergonomic design. Interfaces must be tailored to the specific users to ensure reliable monitoring and critically reliable emergency manual operation. Second, a clear information hierarchy. We have to structure information to present the outline first, the high-level context, to prevent the cognitive overload, that infobesity, that contributed to the AF447 disaster.
Information needs to be organized by priority, not just dumped on the operator all at once.
Precisely. And finally, building in robustness through redundancy. This means using different designs or software to avoid common failures and incorporating things like remote control or supervision capabilities. The designer's meta-task responsibility is to ensure the human user can always make a meaningful inquiry and maintain final, reliable control.
So this deep dive has really shown us the exhilarating high-wire act we're performing daily, balancing the incredible efficiency of automation with the necessity of preserving human agency. We saw success stories, AI drastically improving healthcare, and hybrid systems making manufacturing nearly bulletproof.
But those successes are permanently shattered by failures that emphasize the automation paradox. Accidents are rare, but when they happen, they are catastrophic. Whether it is the operator complacency in the Tesla crash, the information overload that paralyzed the pilots of Air France 447, or the dangerous organizational bias in the Patriot missile system, the central lesson is that automation fails when the human factor is neglected.
And the mechanism to bridge that gap is meaningful human control, which demands more than just a human in the room. It requires both the tracing condition, knowing who is accountable and why, and the tracking condition, ensuring the system responds to human moral reasons.
And we have to remember, the human is not the weak link. The human remains a critical resource for knowledge, innovation, and adaptation. We are capable of responding to the truly unusual circumstances that AI, which is based purely on learned data, just cannot handle. The ultimate example is still the miracle on the Hudson.
Right.
Captain Sillenberger and First Officer Skiles successfully ditched an aircraft with total hydraulic failure using only engine thrust. They adapted. They solved a problem no automated system could handle because that specific failure was unprecedented.
That adaptability, that critical human capacity to manage the unknown, that 1% of novel crises, that has to be preserved.
Which leads to our final provocative thought for you. Philosophers suggest that choices involving genuinely conflicting values are often incommensurate, meaning they're not objectively better or worse, they are simply tragic, value-driven conflicts. Think of complex ethical choices in medicine or difficult personal scenarios.
No amount of data or calculation can logically determine the objectively best outcome in those cases because there is no objective best. It's a matter of values.
Exactly. Even if an AI system could perform calculations 99% better than a human operator, the remaining 1% of decisions, the truly ambiguous, values-driven, tragic choices, must be reserved for human agency, because that 1% is where our moral identity and our collective responsibility reside.
So we ask you, the listener, to look at your own field, at the systems you rely on every day. What are the truly tragic choices that you currently delegate to a machine? And how certain are you that you could retrieve meaningful control if that machine started to fail in a complex, unexplainable way? It's a question of safety, efficiency, and ultimately what it means to remain human in an automated world.